Hello again. It is Jason from STEM Online Tutoring, where we specialize in higher education when it comes to the subjects of mathematics and physics. Whether you're looking for uh, any type of consulting on a question, tutoring classes, or anything else in the areas of mathematics and physics, we are your guys to come to. Okay, so today it's been a while. I've been busy. Hope to be more consistent in my YouTube videos. Sorry about that. For those of you who have been keeping up with my lectures on mathematics and physics, the point of this channel is to help students, whether you're a student in high school or university, or enthusiasts, people who maybe have some background. You need to have at least some background in these topics, math and physics, but who haven't learned a rigorous way of thinking back in your high school days. This is the channel for you. That's why I made this channel, because I feel like the regular education system is not even close to an adequate job in terms of mathematics education specifically. I think it's just beyond a joke. It's not even close to what actual math is, right? Same with physics. Okay, so that's why I have this channel, right? STEM Online is exactly for that. It's to not only tutor tutor students in mathematics and physics, but it's to make sure that they get down into the real uh, rigorous and analytical way of approaching these subjects. Not formulaic, but mainly through developing first critical thinking and then second strong visual spatial skills, because both of these things are important in these subjects. If you understand uh, these uh, these two skill sets, then conceptualizing these topics will become more and more straightforward, right? Okay. Anyways, to continue on, so far we've been doing mainly calculus and logic videos as opposed to physics. Not as much physics. I've made like 3 physics videos, but not enough. We need to do more of those. Uh, because that's what this channel is. It's also a physics channel. So we're going to do physics today. The reason why I want to spend time in math and some logic is because those are fundamental. Those are the foundations that you need to understand physics as well. Okay? Without math, you can't understand physics. Okay, so I want to go to physics today, and I think we're going to work on an interesting problem on calculating the electric field of a charged rod. Okay, so what we're going to do is exactly that. We're going to figure out how to calculate the electric field of a charged rod. Now, this problem is mainly at the level of I'd say an AP level physics, actually higher level AP physics course. So it would have to be some sequence, probably AP, I forget what it is, APC physics? AP, no, I can't remember. But one of the AP courses you'll see this in, or in first year university physics, you'll encounter this type of problem. Okay, it mainly has to do in the section of electricity and magnetism. Okay, so we're going to start this problem. Now, the way to construct any physics problem, if you're unsure how to do them, because at first it can be daunting. Okay, the way to deconstruct any physics problem is different. It's different than math, right? First, draw a diagram. Okay, you need to draw a diagram. You need to see what is happening in a physics problem. It is not math. Okay, so you need to draw the diagram, right, of exactly what you're understanding from the paragraph, from the problem-solving paragraph, and then assign variables accordingly. They either give you variables that they've assigned specifically, or we make up ones where you have to be consistent with those variables. Okay? So we're dealing with a charged rod. Okay, so as you can see here, my diagram, I've already started with a rod. Okay, I have some rod of length L. Okay, obviously I need to define that because it has some length L, rod has length L. Okay, now on the rod, we know that it's charged. Okay, so we can put charges, whether they're positive or negative, doesn't matter. Okay, so plus, let's 1 second here. So plus, let's say plus, just to represent charges. Okay, because if you have an electric field, there has to be charges. Now, I'm going to say automatically here, because we want a piece of charge on this uniform charge distribution. Okay, so since you want a piece of charge, not the total charge, we have an automatic element called dq. dq is a specific piece of charge. One piece of charge. It's not the total charge of the rod. So it's a piece of charge. That's my dq. Now, if that's my dq, okay, then automatically, right, there has to be something else as well. There has to be a dE. Now, dE is the infinitesimal electric field. Okay, I'm going to get to that in a second. All right. Okay, I'm going to put to the side here, actually, some important expression that, if you remember in your notes, if you don't remember exactly, look in your notes, the electric field vector, okay, is equivalent to 1 over 4 pi epsilon naught, all right, times capital Q all over the magnitude of R squared times R hat vector, okay, where 1 over 4 pi epsilon naught is just Coulomb's constant, same thing as K, saying K, okay, Coulomb's constant, all right. Now, I mentioned this dq element. That just means that I have just some small piece of element dq here, okay? Well, if I have a dq, I automatically must have a dE, because if you look in my electric field equation, E is dependent on Q. All right, so if in this case there's a dq, there has to be a dE. But to get dE, that's the electric field vector, we first need to draw a vector from the line of charge, right, from the piece of charge dq. 1 second here. Right, piece of charge dq, all the way to our x-axis here, let's say. Now, where it's intersecting is where the observer is observing the charge, okay? So I'll call this point O prime, okay? O prime will be where the observer is located. 1 sec. Okay, so this is point O prime. All right. Okay, and automatically, the distance from, I'll call this point O, okay, from the intersection point right at the middle of the rod will be point O. So from point O to point O prime will be the x-axis, along the x-axis with length x. And along the y-axis, right, if this whole thing is L, well, we know this is going to be y. Okay, this is my y. Okay, along the y-axis, same thing down here. Right, in the bottom, it will be symmetrical. Okay, now you will notice that this dq to our observer, point O prime, is a vector. Since it's a vector going from dq to prime, well, automatically, right, there should be a vector, that there should be components of the vector, right? So if this is a vector, I'll call it r. That's my vector. There should be an components of this vector. Right, so r1, let's say. Okay, here's my r1 vector. And here is my r, I'll call this r0 vector. Okay. Next thing to do is to notice a relationship here, an algebraic relationship. We can do head to tail and get an expression, right? So because we know that r1 vector plus r vector is equal to r0 vector, right? R0 vector, right? If you look carefully head to tail, r1 plus r vector gives us r0, right? R0 vector, okay? Therefore, if we rearrange, right, for r vector, we want to know what r vector is because we want to eventually determine what the magnitude of r vector is, okay? So figure out what r vector, so r vector has to be equivalent to r0 minus r1. Okay, so now we have that. Then we need to determine, since both r0 vector and r1 vector are vectors, we need to figure out the expression in terms of the components of those vectors. So first, let's figure out what r0 vector, if you look carefully, is only on the x-axis. So that means in terms of vector components, x, 0. Okay, and let's look at y vector, so second thing to do is look at r1 vector. So r1 vector is in the y direction only, so this is going to be 0, y. Now we need to determine r vector. R vector is r0 minus r1 vector. We'll get in terms of x and y. Right, so next, get r vector. R vector is equivalent to r0 minus r1, so subtract. So this is going to be x, 0 minus 0, y. And this is going to be equivalent to, let's see here, x minus 0. Do it component-wise. The x components subtracting, y components subtracting. 0 minus y. This is going to be x, negative y. Okay, so this is r vector. Next, since we know what r vector is, notice we need to get the magnitude of r vector. Okay, so we know that by Pythagorean, so by Pythagorean theorem, because this is a perpendicular triangle, and we're finding the magnitude, so we have the Pythagorean theorem here. We know that r, magnitude of r squared is equal to x squared plus y squared. So we'll substitute that in. Okay, so we already know what 1 over 4 epsilon naught is, what q is, we know what r squared is. We'll figure out what r hat is. Yeah, we also need to determine what r hat is in terms of x and y. Next is r hat. Okay. Now r hat, right? R hat is equivalent to the following. Okay, r hat is equal to r vector all over the magnitude of r vector. That's what a unit vector is. The vector divided by the magnitude of the vector. Now we know that r vector is equivalent to x, negative y all over the square root. Because after the square, there's now square both sides. Isolate for r vector, you get square root of x squared plus y squared. Okay. No, that's quite a bit, but that's what we have right now. So mathematically, we've got that done. However, though, we need to go back to our charge distribution on the rod. Now, the rod, right? On my rod has charges along the distribution, because it's a charge distribution. We have an element, each piece of charge, dq, right, that we have to deal with. Okay, now, since there's a piece of dq, there's also a differential electric field vector. And that field vector comes out of where the observer is observing. So it's going to be right over here. Always. This is my DE. 1 second here. Automatically, I have a DE vector. Okay. Now that's my DE. Alright. Now, since I have a DE vector, automatically I have an x component and a y component, because any vector has x and y components. So we have this guy over here. This is my dEx. And we have a dEy. Now, this dEy has to be in the negative y component of the electric field because it's going downwards in order to make up that sum component, sum vector of dE, right? dx goes to the right, dEy goes down. Now, what ends up happening is that by symmetry, right, since we have elements of dq all over our charged rod here, okay, since we have dq elements all over our charged rod, right, that means we have our electric field all over this charged rod. Okay, so automatically, when there's electric field all over the charged rod, you're supposed to draw a vector from the charged rod to where the observer is. So just like in the top, we do it at the bottom. Okay, like this. Go directly. The vector should be going directly, intersecting where the observer is, and reflect out like that. You'll notice automatically, by symmetry, in order to have this vector come out, there has to be a positive dEy. Okay, dEy. And you see the positive dEy and negative dEy is canceling. So there's no y component of the electric field that we need to look at. Okay, so we need to calculate. So we need to look at calculating dEx. So we're going to look at the x component of the dE. So this is going to be dEx is equal to 1 over 4 pi epsilon naught, right? 1 over 4 pi epsilon naught times dq, because everything is in terms of differential element, piece of element here, all over magnitude of squared. And we know that's going to be equivalent to x squared plus y squared. Okay, so this is going to be x squared plus y squared, times r hat. If you look at r, now this r hat, though, is in the x direction, by the way, only. So look at our r hat vector. Oh, we're only looking at the x component here. That is only this piece right here. Okay, that piece is what we're going to get for our x component. So doing that, we're just left with the following. Okay, so we're left with multiplying by x all over the square root of x squared plus y squared. Okay, simplifying, we get dEx is 1 all over 4 pi epsilon naught, right, times the dq, x dq, all over x squared plus y squared, okay, x plus y squared, to the 3/2, right, simplifying the fraction there. Then from over here, we have another issue. We have an x dq here. This doesn't tell us much because we want to be able to calculate the total electric field here, and the only way to do that is to integrate. And the only way to integrate is to make sure that we're integrating either with respect to x or y, depending. But we don't know yet because we only have a dq element here. Look carefully at our rod. Our rod is in respect to q and length L. So we have to deal with a continuous uniform charge distribution with respect to length. Okay? All right, so that means that dq, if you remember, since q over L is the uniform charge distribution, is equal to dq over y, rearrange for dq. dq is equal to q dy over L. This now tells us that we're going to be integrating with respect to y, so we substitute the expression. Substitute. So you can see how logically I am substituting things in back and forth. Okay, so substitute. 1 second. My L looks like a 2, sorry. That's an L. Okay, substitute back into this guy over here. When I mean substitute back into this. Okay, so now I get my dEx, right? The EX equals 1 over 4 pi epsilon naught times x times dq. dq is just going to be q dy over L divided by x squared plus y squared 3/2. Okay, and then dEx is equal to, right, 1 over 4 pi epsilon 0, okay, times x times q times dy all over L times x squared plus y squared to the 3/2. This is a bad pen. Got the 3/2. Okay. Then from here now, right, what's going to happen is put this all over a common denominator. So dEx is equal to x times q times dy all over 4 pi epsilon naught times capital L times x squared plus y squared to the 3/2. Okay, integrate now, because we want to figure out the total electric field in the x direction. And right now we only have a piece of the electric field. Piece of electric field dE. That's why I called it dE, because you only have a piece of an electric field in order to have a piece of the electric charge. Each piece of electric charge distributed on the on our charge rod. So we have a continuous charge distribution here. So we need to integrate to solve for EX. Okay, so integrate now. So move over here. Okay. So what I'm going to say here now is we're going to now we have to integrate. Integrate to isolate for EX. So EX equals the integral. Like my integrals look cool. Okay, so integrate. Okay, so we have the integral of xq dy. Right, so xq dy all over 4 pi epsilon naught 4 pi epsilon naught times x squared plus y squared to 3/2. Okay, that's where we're integrating. Now, we need to know the limits of integration. If you look carefully at the problem, back in the geometric diagram, we're going, look at our rod is vertical, right? So radiating out of point O, right, you'll notice that this is length y. This is also length y symmetrically, right? Okay. Now, if this is y and this is y, right? And this whole thing is length L, as I labeled, right? Then that means my little y down here is negative L over 2, right? Half the length of the total length, okay? The upper part has to be positive L over 2. Has to, right? Because L over 2 and L over 2 gives us the total length L of the entire entire length of the charge rod, okay? All right, so this has to be the lower limit of integration minus L over 2. Upper limit of integration is L over 2. Okay, and then we are now ready to integrate this. However, though, I'm going to get you to integrate it. So this is going to be a challenge video for you to practice both your physics and mathematics on this problem. Okay, so try and integrate this. And I'd like to hear what your solution is. Tell me your thought process in the chat below. Or you can email me, or for anything else, you can contact me. I have my information on my page, right? So I hope you found this video interesting and helpful. Don't forget to like and subscribe. and there'll be plenty of more of math and physics videos. Okay? Always willing, and it's my pleasure to be educating you on the most advanced concepts. Until next time, bye bye.